Greetings and hello to everyone watching. We are from Pi-thons group and our topic for our discrete mathematics assignment is Bayes' theorem. Our team consists of 6 students from computer science. Here we have Chua Kheng, Haarinesh, me, Nigel, Jeffery, Chia, Chang, Yong, and last but not least, Amaro. Our presentation consists of 5 parts, which are introduction, history, application, biggest impact, and conclusion. Let's start off with the introduction to our topic. Probability is a branch of discrete mathematics that describes the likelihood of an event to occur, or the likelihood of a proposition to be true. Conditional probability describes the probability given condition that another event has occurred. One of the formula that can calculate conditional probability is Bayes' theorem. This theorem calculates conditional probability by incorporating initial knowledge of other conditions that could be related to the event. This theorem is applied worldwide in our daily lives, especially in healthcare, to predict the likelihood of an infection or drug usage. Now I will pass to Jeffrey for the history.
Thank you, Nigel. In this part, I will talk about the history of how Bayes' theorem was introduced. If you look at your left, that's Thomas Bayes. In the early 1700s, Bayes came up with a concept and wanted to figure out a way to accurately predict a future situation where not much info was given. He spent the rest of his life trying to prove his theory, but he passed away in 1761, and his theory was laid out cold until the arrival of Pierre-Simon Laplace. So on the left, this is Laplace. Laplace rediscovered Bayes' theorem independently by himself. However, he has a more different approach onto the concept where he states that the principle is not with an equation, but in words where it is the chances of a cause is proportional to the chances of the event. So basically, he said that Bayes was too focused on giving a universal equation where what matters most is the context of the situation, which is the event and conditions. And with this, Laplace spent his next 40 years trying to prove his principle, and on the late 1700s, his discovery was able to develop Bayes' theorem into what we call now conditional probability. Now, I will explain Bayes' formula. Based on the formula above, it states that the conditional probability of an event B based on the occurrence of another event A is equal to the likelihood of the second event A given the first event B multiplied by the probability of the first event B divided by the sum of the probabilities of the data in all possible events. I also want to emphasize that the sum of the probability of the data in all possible events, which is the bottom part, is also equal to the probability of A. So now I will pass to Chang to talk about the applications of Bayes' theorem.
Thanks, Jeff. It then brings us to the application of Bayes' theorem in everyday life. Weather forecasting is a common application of Bayes' theorem. We can improve the precision and reliability of weather forecasting by employing the Bayes' theorem. Here's an example of how Bayes' theorem can be used in weather forecasting. Before going out, you ask Alexa, a virtual assistant technology, the weather, and are told it is going to rain. You are upset and decided to investigate. Sources indicate that Alexa has correctly predicted 90% of all rainy days and 80% of all dry days. Assume that the place you live rains once every 10 days. So let E be the day Alexa has predicted rain and let F be the day it actually rained. In this case, we should calculate the probability of 4 scenarios, which are the probability of it actually raining on the days we have a rain prediction, the probability of it has not rained on the days we have a rain prediction, the probability of it actually raining on the day we don't have a rain prediction, and the probability of it has not rained on the days we don't have a rain prediction. Let us examine the question. The question stated that the place you live rains once every 10 days, meaning that the probability of it raining is 1/10 or 0.1. And by subtracting 0.1 from 1, the probability that it does not rain is 0.9. Alexa predicts 90% of those rainy days according to the sources, which is the probability we will have a rain prediction on the days it actually rains is 0.9. Rainy days that have not predicted by Alexa, by subtracting the probability we will have a rain prediction on the days it actually rains which is 0.9 from 1. The probability that we will have no rain prediction on the days it actually rains is 0.1. In 100 days, 90 days did not rain. When it did not rain, and Alexa predict 80% of all dry days, meaning Alexa predict 20% of all dry days are not dry. The probability that we will have a rain prediction on the day has not rained is 0.2, and by subtracting 0.2 from 1, the probability that we will not have a rain prediction on the day has not rained is 0.8. In 100 days, it rains 10 days. Alexa predicts 9 of those rainy days. The remaining 90 days, when it did not rain, Alexa predicts 20% of them are not dry. This means that 18 days were wrongly predicted because 90 multiplied 20% equals to 18. 9 accurate predicted days plus 18 wrongly predicted days equals to 27 total days of rain prediction in 100 days. The probability of getting a rainy prediction regardless of whether it actually rains is 0.27. Probability of Alexa saying it won't rain is 0.73 by subtracting 0.27 from 1. We will calculate the probability of it actually raining on the days we have a rain prediction for scenario 1. By applying the formula of Bayes' theorem, the likelihood of it raining on the days we have a rain forecast is 0.3333 or 33%. For scenario 2, we will calculate the probability of it has not rained on the days we have a rain prediction, and we will get 0.6667 as the likelihood that it will not rain on the days for which we have a rain forecast. Next, for the third scenario, we will calculate the probability of it actually raining on the day we don't have a rain prediction. As shown in above, the likelihood of it raining on the day we don't have a rain forecast is 0.0137. And lastly, we will calculate the probability of it has not rained on the days we don't have a rain prediction for the last scenario. We can obtain 0.9863 as the likelihood of no rain falling on a day when there is no rain forecast. Now I will hand over to Kheng.
Thank you, Yong. Now I will be talking about the application 2, which is COVID-19 screening test. For your information, this is one of the applications under the medical field. Description of application. First and foremost, as Alex is the close contact with several COVID-19 patients, hence he is quite worrying about his health condition. Based on the information provided, we found that 42,000 out of 100,000 people in Malaysia is expected to infect with COVID-19. At the same time, the second information provided is the test kit used by Alex has 90% of sensitivity and also 80% of specificity. So now we will let E as someone that is tested positive, while we will let F as someone that is infected with COVID-19. So for your information, later we will be looking about the four scenarios, where the first scenario will be the probability of Alex is infected given that he is positive. The second one will be probability of Alex is not infected given that he is positive. The third one will be the probability of Alex is infected given that he is negative. And lastly is the probability of Alex is not infected given that he is negative. So just now, one of the important information provided is 42,000 out of 100,000 people in Malaysia is expected to infect with COVID-19. Hence, from here, we know that the probability of someone being infected with COVID-19 is equal to 21/50 or 0.42. For the probability of someone that is not being infected, it can be calculated by subtracting 1 with the probability of someone that is infected with COVID-19, and in this situation, finally we will get 0.58. Next, our second info is the sensitivity of the test kit, which is 90%. Okay, so now what is sensitivity? For information, sensitivity is the rate where the test kit will correctly identify the positive result. Hence, the probability of someone tested positive given that he is infected is 0.9. On the other hand, for the probability that someone tested positive given that he is not infected is 0.1, and we can get this value by subtracting 1 with 0.9. Furthermore, our third info is about the specificity of the test kit, which is 80%, and just to let you know, specificity is the rate where the test kit will correctly detecting the negative result. So basically, sensitivity is about the positive result, while the specificity is about the negative result. Okay, back to the question. So the probability of someone being tested negative given that he is infected will be 0.8, as the specificity is 80%. Next, to determine the probability of someone tested negative given that it is not infected can be calculated by subtracting 1 with 0.8, and finally we will get 0.2. So the last info is about the probability of someone being tested positive using the test kit, which is PE. First, we assume that there are 100,000 people, 42,000 people is infected, while the other 58,000 people are not infected. Out of 42,000 people that is infected, as the sensitivity of the test kit is 90%, there will be 37,800 people that is infected are tested positive. Next, as the specificity of the test kit is 80%, hence 20% out of 58,000 people that is not infected will get a positive result too, which is known as false positive. So in total, considering the true positive and the false positive, there will be 49,400 people that is tested positive. Hence, the probability of someone being tested positive using the test kit will be 0.494. On the other hand, by subtracting 1 with 0.494, we will get the probability of someone being tested negative, which is PE prime, and the value will be 0.506. Now, we look into our first scenario, which is the probability that Alex is infected given that he is positive. So basically, there are two methods of calculation where we will calculate the product of the probability of someone being tested positive given that he is infected and the probability of someone being infected. And lastly, we will get 0.378. Next, we need to take the 0.378 and divide it by the sum of 0.378 and the product of the probability of someone being tested positive given that he is not infected and the probability of someone that is not infected. And finally, we will get 0.494. Alternatively, we may also divide it directly with 0.494, which is also the probability of someone that is being tested positive. In a nutshell, what we will get is the probability of Alex is infected given that he is tested positive is 0.7652 or about 76.52%. For scenario 2, we can calculate the probability of Alex is not infected given that he is positive by applying the same concept of calculation. Alternatively, we may also use the third method, which is the fastest, by subtracting 1 with the probability of Alex is infected given that he is tested positive, and finally we will get 0.2348. For scenario 3, the concept of calculation is same as what shown and explained previously. And according to the calculation in this slide, the probability of Alex is infected given that he is tested negative is 0.083 or around 8.3%. Lastly, in scenario 4, the probability of Alex is not infected given that he is tested negative is 0.917, and we can just easily subtract 1 with the probability of Alex is infected given that he is tested negative, and we will get this number. Basically, that's all from me, and now I will pass to my teammate Hari.
Thank you, Kheng. Now I'll be highlighting two of the biggest impact of Bayes' theorem to the human life, including weather forecasting, which is very important especially for the people that their works are really depending on the weather, and COVID-19 screen test in medical field. First and foremost, weather forecasting. Weather forecasting is a science or skill of anticipating weather patterns. The major contribution is to produce accurate prediction about the status of atmosphere over a short period of time so that people can make judgments about their actions. Not only that, weather forecasts allow organizations and individuals to avoid weather-related incidents and improve quality of life. Next up, we will look at the second application, which is COVID-19 screening tests in medical field. For information, there are several types of COVID-19 tests available, which are RTK, PCR, and COVID-19 antigen self-test kit, and all of them require nasal or throat swab sample. Scientists usually determine the diagnosis value, including sensitivity and specificity, for the diagnosis test and make the decision whether the diagnosis test is suitable to be introduced, used, and applied. Now, I will pass to Amaro for the conclusion part. Thank you.
Thank you, Haarinesh. And so now we have come to the last part of our video, which is the conclusion. To summarize, the Bayes' theorem is a versatile mathematical formula applied in various fields. It finds its uses in any field that relies on probabilities, becoming an essential part of statistical analysis of many studies and research. In modern society, the Bayes' theorem has numerous applications. For example, weather forecasting. Determined by meteorological parameters, a weather forecast is made accurate by combining and calibrating multiple factors as well as from other past and present forecasts. The Bayes' theorem can also be used to calculate the probabilities of outcomes of a COVID test using existing numbers. This applies to any medical test in which the Bayes' theorem can be used to calculate the probabilities of false positives and false negatives. At that, the Bayes' theorem is evidently an impactful concept that has greatly contributed to humanity. With that, we have come to the end of our video. Thank you for listening, and we would like to give special thanks to Sir Jale for the guidance and knowledge that he has provided to us throughout the duration of this assignment.